We are live, sir. Please start.
Okay, so welcome to the live session for Computational Electromagnetics. This is a time for students who have been enrolled in this course to have their doubts clarified or have any other questions about computational EM apart from the lectures. Want to get them clarified? This is a good chance. So let's see. If you have a question, please unmute yourself and ask, or type it into the chat box. Yes, Arun, I believe. I see a few students are online. I see Sunita, Arun, and Anant. Right. So before more students come in, if you want to ask your questions, now is a good time.
Hello, am I audible, sir?
Yes, Anant, go ahead.
Good evening, sir.
Good
Sir,
evening.
my doubt was from week 2 last lecture
Mm-hmm.
when we were solving Helmholtz equation.
Okay.
So I was doing it again and again, but in the last part of the equation where we have written phi I minus something, which is equals to 0 for one case, and when r prime is not equals to r.
Mm-hmm.
So in that case, I was having an issue with the minus sign. I was having a minus sign with the in front of phi I also,
Mm-hmm.
but in the lecture it was only plus. So I was not getting it.
Okay, so you're talking. This is let me get the lecture right. You're talking about the Green's function development, right?
Yeah, the last part, sir, very last part.
Okay, very last part. So you have the Green's function, and you are in the way that you derive it. You're saying that you're off by a minus sign. Is that it?
Yes, sir.
Yeah, actually, yeah. So the thing with minus sign, it's very easy to go wrong with minus signs because it depends on the sign convention which you choose. For example, in the definition of the Green's function, you have on the left hand side you have your del squared g plus k squared g, right? And on the right hand side you have your delta of r minus r prime. In some books, the convention is a minus delta on the right hand side, and in some books, the convention is a plus delta on the right hand side. Okay, and depending on that convention, you may or may not get a minus sign in the final result which you get. So what I would suggest is if you've done your derivation carefully with a conscious decision of having a minus or not, what result you get should be fine. It's even possible that there is a minor sign mistake in during the live lecture.
Okay, no problem, sir.
Yeah, you'll find equal number of resources with having the plus sign and the minus sign. So when you read a paper, it's always very confusing that is this what sign to take. So it's better that you derive it from scratch yourself, and then you're confident about what sign should be done.
Okay, sir. Okay.
Hello, good evening, sir.
Yes, good evening.
Am I audible?
Yes.
Good evening, sir. Thank you for your lecture, sir. Sir, I have two doubts. One is I'm always confused with that r and r prime. In some cases, the integral is done by taking r prime as a variable, and in some cases r as a variable. So this in all the cases, whether any r prime is taken as the source position vector and r is taken as the field position vector, or how we can easily identify which part to be which variable to be
chosen for either purpose.
Chosen
right?
for integration.
Correct. So, okay, so that's a good question and also a common cause of confusion. So, when you look at your, the solution to your wave equation, so you would get something like phi is equal to phi I plus the surface integral. Now,
Yes.
right? So, and the question is, what should I put a r or should I put a r prime? So, the
Yes, sir.
simplest way is to first stand outside the integral sign. So, as a user, I'm standing at some position in space. So you decide beforehand that is your regular outside space primed coordinates or unprimed coordinates. In the lecture content notes which I have shown, in that I have chosen the primed coordinates to be these, the world outside. So that's why you will see that the phi term will be phi of r prime. So you will see phi of r prime is equal to phi of I minus this integral. Now, so in some sense, you can say source position is r prime, if or rather the observation position is r prime. If I have the moment I have chosen the primed coordinate to be the outside position, so I have to choose the other variable, which is the unprimed coordinate r, for the variable of integration. Okay. Again, as I was saying in my answer to the previous question, this is not a universal convention. In some books, you will find it flipped. So r will be the observation position and r prime will be the variable of integration. Okay. So there is no hard and fast rule about it. The trick to identify it is that look for the term outside the integral.
Okay.
And the other term will be inside, will be the variable of integration. That's all.
That means when we take that Dirac delta function, that if r prime is included in the integration space, we say that value gets to 1. I mean the function value.
Okay, so for the Dirac delta function, life is a little easier because it has both r and r prime.
Yes, sir.
You don't have to worry about what. Now, when I have both r and r prime and I have an integration that is happening, when I have an integration that is happening, I have to choose, what is the domain of integration. I can choose to integrate in V1, I can choose to integrate in V2, or R1 and R2. That's my choice. Right? Okay, sir. So now I decide beforehand where my observer is going to be. So if I decide that my observer, which is given by the r prime coordinate, if my observer is in, let's say, R1, but my region of integration is R2, then my delta function is always 0, right?
Yes.
So then that is 0. So that's how you decide beforehand where you want to place the observer, and you make the two separate cases that way, and then you will have no trouble.
Okay. One more question, sir.
Yes.
Sir, in that while deriving that integration part, you made that observer position to be, I mean the source position to be fixed at the origin of the coordinate, so that the theta becomes invariant. Theta is not variable. We can easily write as 2 pi into that integral.
Can you remind me which particular?
That is in scattering problem, sir. Scattering problem. When we are solving that problem in a two-dimensional case, we told that if we take r prime is equal to 0, then what happens? What happens is that theta will, according to the observer, if we round, I mean, if we walk through the theta, there won't be any change. It will be unique. This happens in the V1 region as well as in the V2 region.
So this is to sort of derive the wave equation. To derive the polar coordinates solution.
Yes, sir. Over there. 2D polar coordinate.
Yes.
So in one case, in V1 case, told that the origin of the coordinate system we'll put at the r prime, so that theta will be getting invariant.
No, so let me stop you right here. I think there's a little bit of confusion. So the place where we are saying that you place put r prime at the origin, and therefore it becomes invariant with respect to theta. That was a derivation to compute the Green's function, right?
Yes, sir.
Now, when I'm interested in purely computing the Green's function, I need not think of region 1 and region 2. Let me think of the entire space filled with some wave vector k.
So that Green function is valid for both the, I mean, phi1 and phi2. So it is same green function we can use.
It is, well, it is not exactly same. What is
Okay.
different is that the region 1 and the region 2 have different values of k.
Yes, yes.
So the
Yes.
form is
Constant.
the same. Yeah,
Yes.
the constant which
That
is,
operator will be same.
the operator is same. Again, the operator has the k value inside it. So strictly
Okay.
speaking, the operator is also not the same because the
Okay.
k value is sitting inside the operator, but the solution looks almost the same. So your Green's function which you get, which is for example Hankel of k into r. So when k is different, the Green's function is different.
Okay, so that means there is no, I mean, the Green's function is derived for one time, and in the two problems we are using it by varying the k alone.
By changing, yes. So that is that is a special kind of Green's function, which is called the free space Green's function.
Okay.
Right.
Okay.
It's not that every Green's function is going to look like this. I can derive a Green's function where half the region is k1 and the other half of the region is k2.
Okay.
That is possible. The solution is not some closed form expression which we got nicely. It is something very complicated. So those kind of Green's functions are also possible.
Okay, sir. Thank you, sir. Thank you.
Yeah. Just remember the basic funda of what is a Green's function.
Okay.
Green's function is derived as a solution to Helmholtz equation with an impulse function on the right hand side.
Yes. It's a response to impulse input.
Yes.
Okay, sir. Thank you. Thank you very much.
There was a question from Sunita, which I saw in the chat. Says, "Good day. Would the exam be physical or online? I want to register for another course exam on the same day." Well, I think given the way everything is going in the country, I would imagine it's going to be online. But the NPTEL staff are much more fine-tuned to the situation, whether the TCS centers will be functional by the time the exam period comes around. So I don't want to take a guess and then have them correct me. So I will have them, if they want, they can unmute themselves and respond right away since they're also on the chat, or they can, they'll send out a clarification on the forum very soon. Okay, Sunita? Okay, I think we have run out of questions.
Hello, sir.
Yes, Anant, go ahead.
Sir, I want to ask one thing which is not related to this. I mean, not exactly related to any lecture, but in general.
Okay.
Is it a matter of research that we use some kind of functions to integrate some integrals and some other kind of functions to integrate some other integrals? I mean, like we use the Green's function to integrate the Helmholtz equation for getting the solution. So, I mean, how do we get to the point when we are able to think independently? Yes, we will use this kind of function to integrate this or something like that.
Well, so I'll tell you this. One thing is a little misleading is that we showed you the derivation of a Green's function for free space, and that looked like a simple enough derivation. So actually, good news ends over there. If the moment you go to a more complicated situation, there are very few Green's functions which can be used. For example, there is a Green's function for two half spaces and a few other Green's functions. But for the most part, that's it. That there's not much more you can do about it. So the research or innovation in trying to find new Green's function is, at least to the best of my knowledge, is not very much. And whatever is there is well documented. Beyond it, when practical situations are more complicated, then you have to solve these things numerically. You're not going to derive any closed form expression. And the main focus of research in this field is then to find out different strategies by which the solution to these equations can be made faster. So, if you just do naive matrix inversion, you know that the complexity is roughly order n cubed. Then there are some innovations where you recognize some structure in the problem and you can use a conjugate gradient FFT method to speed up the calculations. That takes it from n cubed to something like n log n, and so on. So there are, over the last 2 decades, there have been some very many innovations which will help speed up the solution. So the focus has shifted from trying to find Green's function, which was long ago, now to saying, okay, we have this, let's try to make it as fast as possible. Okay.
Okay. Yeah. Thank you, sir.
Yeah. Okay. Another question: on what basis variables we decide which domain to select for evaluation and which solution would be better suitable? Not fully clear what your intent is. On what basis we decide which domain to select for evaluation and which solution will be better solution, will be better suitable. So if you notice that in the derivation of the actual integrals which you have to solve, there is no choice which you had. You had to choose both region 1 and region 2, then use the extinction theorem for both the regions, and you get your system of equations. So there is no choice for you that should I choose this or should I choose that region. You have to choose all the regions. In the example we took, there were 2 regions. In another example, there can be 3, 4, or n regions. So you have to choose each region one by one, find out the extinction theorem for each region, write down one equation from each region, and then solve it. Where you have a choice is in choosing the kind of basis functions. So again, the example which we took was of a simple pulse like basis function, but you can choose a triangle basis function, you can choose sinusoidal, you can choose any other kind of complicated functions, and that's for the basis functions. Similarly, for the testing functions, when we're talking about method of movements, you can choose something other than delta testing, and these are the factors which would actually make you get a better solution. Better meaning more accurate, less time. That's what we're looking for. Sometimes if you want more accuracy, then you have to sacrifice time. So those are the real design choices, not which domain to select. Okay. I hope that was clear. Arun has a question.
Sir.
Yes.
Actually, we have brought 2 sets of equation while solving the 2D scattering problem.
Right.
One is with phi1 as the solution. Other one is phi2 as the solution.
Right.
In the first setup, using phi1, we got Huygens principle and extinction theorem.
Yes.
In first case, it was like incident field minus scattering field will be the phi1.
Yeah.
And if the observer is inside the object, he will not find any field that is coming from incident. Incident field.
Mm-hmm.
And in the second case, we are considering the observer to be inside the object,
Mm-hmm.
and we are solving for phi2. So
Mm-hmm.
I am confused that if we approach the problem from in total,
Mm-hmm.
physically, what are the exact field exist inside object and outside object?
Correct.
Is it
Good
phi1
question.
and phi2?
Correct. So to give you a very simple answer, the physical field, if you went in with like a device which measured the field, is phi1 in region 1 and phi2 in region 2. Okay. Everything else is mathematics. So when I took, for example, the first equation, which was the Green's function for region 1.
Yes, sir.
There my integration obviously is, it happened over region 1. Yes. And because it happened over region 1, I had a choice where to place my delta function, either inside or outside. That gave me Huygens and extinction for region 1. Similarly, when I did the integration for region 2, I have a choice where to put the delta function, in or out.
Okay.
And that gave me 2 equations. Now from those 2 equations, I pick one from each. For example, I can take the extinction theorem from each of them. And when I do that, what are the variables that I have? I have phi1 in one equation and phi2 in the other equation.
Yes, yes.
But if I choose the variable of integration and the source point both to be on the same contour, then continuity of equations will say that phi1 is equal to phi2, grad phi1 is equal to grad phi2, or related by the permittivity constant, depending on what polarization you take.
Nice.
And so that helps us to eliminate phi1, phi2 and replace it by just one. Let's call it just phi. And we solve for phi and grad phi.
Okay. So
physically, it's phi1 and phi2.
Okay, like as you said, like if you measure using a device, I'll find phi2 inside the object and phi1 outside the object.
Yes, yes, absolutely.
Okay. So what about, I mean, like saying that an observer is outside the object.
Yeah.
And he feels that the object is not present there. Like sources are sitting on the boundary and emitting. So like for his mathematical concept only, we are saying the object, the field inside object is 0.
So it's what you're asking is slightly counterfactual. You know what the word counterfactual means?
No, sir.
Counterfactual means it's a kind of a something which you can never do in practice, but you still make a guess about it. So, for example, if a observer is standing outside in region 1, he or she can never go inside the object.
Okay. Like as you said about that game, like is this surface equivalence theorem?
This is exactly surface equivalence theorem. Right? So for an observer standing outside in region 1, he or she will observe 2 fields coming. One is from the incident field from the source, and the second is the scattered field, from the object. For the observer, if you could magically make this observer go inside object 2, then inside object 2 you have the second region equation, which would be the contribution which is coming from all the secondary sources on the surface. That's all.
It is like someone is telling, as you said in that game, someone is inside the object and saying that there is no field.
No. Inside the object, the person will observe a field equal to phi2.
But he is lying. I mean, in first case of first observer, he is saying that there is no field inside the object.
That's not what is happening. That is not. So that is what that statement which you're looking at, which is the extinction theorem for region 1. That's what.
Yes.
That is what is confusing you. What that is saying is that for an R prime which is inside the object, the incident field and the scattered field somehow seems to cancel off.
Okay.
Right. That's why I get a 0 on the right hand side. But that's a mathematical statement. That does not physically mean that the field is 0 inside.
Okay, so the first observer have no device to go inside and measure. So mathematically, he assumes that the field is 0.
Mathematically, it's only a mathematical statement. If you actually take an observer and go inside region 2, that observer will measure a field equal to phi2, not 0.
Because he has got the Dirac delta function inside.
Yes, where we were considering the Huygens principle for region 2.
Yes. There is no incident field, but
exactly. That's the only difference between observer 1 and observer 2. For observer 2, there is no incident field, but only field from the surface sources. For observer 1, there is both incident field and secondary sources. That's
so the extinction theorem for observer 2 will be whatever the scattered field that cancels, I mean, that is 0.
Exactly.
0.
0 outside.
Yes. No scattering is happening outside the boundary.
Yeah, mathematically.
Mathematically.
Yes, sir. Mathematically.
Okay, clear, sir. So if I found phi1 and phi2, my problem is solved.
Actually, I don't even need to find phi1, phi2. I need to find
phi which is continuous.
On the boundary. Okay. Once I find it on the boundary, then I can use the Huygens equations and tell you the field anywhere.
Fine. So finally in my hand, I will have a phi. which will follow all the boundary condition.
Yes.
And individually someone ask find the field inside object, means I'll use the Huygens principle and put and find phi 2.
Yes, absolutely.
Okay.
You got it
Okay.
right.
Thank you, sir.
Sure. Okay, I think we have exhausted the questions that we had for our session so far. You all have my email address and the course discussion forum available. So really, I encourage you to ask questions on the forum or directly to me. We'll be more than happy to clarify. This is not an easy subject, so it'll take time, but stick to it. Thank you, everyone.
Thank you, sir.